Welcome back. So, last lecture at the end of last week we saw that the normal depth we found out in this particular question was 1.5 meter, although the problem in itself was very simple and easy, but the calculations was very complex. But I hope this has given you a good idea. Now, we are going to solve another question at the beginning of this lecture itself, and it says a trapezoidal channel has a bottom width of 10 meter, okay, and a side slope of 1.5 horizontal is to 1 vertical. The Manning's n is also given as 0.015. Now, the question is, what bottom slope is necessary to pass 100 meter cube per second of discharge in this channel at a depth of 3 meter. See, on all these questions, the formula is Q, the whatever is 1 by n area into R h to the power 2 by 3. You see what all things are given, n is given, okay. You have been given area also, because you have been given a bottom width, side slope, so area is known. So, everything is known, so hydraulic parameter. So, in this particular question it is about finding S naught. This is a broader, I mean a simpler way to look at the problem. So, what exactly is being asked? So, we start doing this question. So, a trapezoidal channel, very simple. So, this is 10, this is 3, this is 4.5. So, area is 10 into 3 plus half base is 4.5 into 3, okay, for this one, and plus same is for this one into 2. So, area is going to be 43.5 meter square. So, what is given is correct, all right. And the wetted parameter, the same thing, this is 10 plus 2 into whatever this length is, all right. So, this is 3 and this is 4.5, all right. So, this length we can find out, okay, because I think they have taken it in terms of this slope. So, that is why this, but this will come 10 plus 2 into wetted parameters under root 3 square plus 4.5 whole square, okay, and that will come to be 20.81 meter. Perimeter is also correct, all right. Therefore, hydraulic radius is A by P. So, 43.5 divided by 20, that is 2.09 meter. So, we have been able to find out area, we have been able to find out parameter, we have been able to find out the hydraulic radius, all right. So, by Manning's formula, Q is 1 by n A r to the power 2 by 3 S naught to the power half. Q we already know, n is already being told to us, area we have already found out, hydraulic radius we already found out, 2.09 into 2 to the power 2 by 3 by dividing A by R, sorry, A by perimeter. S naught is something we do not know, okay. So, this comes out to be 100 is equal to 4740 into S naught to the power half, and if you calculate, S naught will come out to be 4.451 into 10 to the power minus 4. So, this is one question. So, we have seen in Manning's equation, we have seen we were given everything, we were asked to calculate Q in one problem, okay. In the other problem we were not given Y, so we were asked to calculate Y. Here we have been asked to calculate S naught, but the procedure remains the same. First you find out the area, you have to find out the wetted parameter, P is wetted parameter, Okay, in assignments I will give you the type of questions that will be expected in the exam, a shorter one basically, not taking too much I mean complex problems. Okay, and then when you know A and P, then you find out RH in every problem. You look up the tables, or if n is given, you should be able to find out S naught from either the questions or if sometimes it is given. Okay. All right. So, we move to the next question. So, a circular drainage pipe of 0.80 meter in diameter conveys discharge at a depth of 0.30 meter. If a pipe is laid on a slope of 1 in 900, so we have already been given a slope, correct? Estimate the discharge, we have already been given n. Now, the complexity of this problem is that our pipe is no longer, our channel is no longer rectangular, it is circular. Okay. So, how to deal this problem? So, most importantly, you have to always find out the area and the wetted parameter. This is a circular drainage and it will look something like this. Okay. So, the D is 0.8 meter and Y is 0.30 meter, all right. Okay. Fine. So, the area of the flow section shown here, you see this area of the flow section has to be calculated in terms of these angle theta, all right. And this will be the area of the sector OMN minus area of the triangle OMN. So, if we for this area, if we find out the area of this, which we can easily find out in terms of this angle theta, and subtract this area of the triangle, we should be fine. Okay. So, this is how, and the same is with the parameter we will be able to, this is the wetted part and this is the wetted parameter. Now, the question is how to be able to find that. So, as I said, area of the sector OMN minus area of the triangle OMN. So, this sector, area of the sector OMN is very simple, half r square into 2 theta. Okay. All right. If this is theta, so what is 2 theta? So, okay. So, if this is theta, this one, so this is 2 theta. Okay. So, this is what it has been used here, minus area of the triangle is half base into height. Okay. So, you see base, this is base into height, if this is r, correct. So, this is r sin theta, and this, if this is theta, and this is r cos theta, correct. So, we get area as d square by 8 2 theta minus sin 2 theta, all right. Also, we know that cos theta can be written in terms of d and y, d is the diameter, for example. So, here we use r naught, but actually we have finally turned this in terms of diameter d. Cos theta is simply d by 2 minus y, so if this is y and this is d by 2, so d by 2 minus y will be this length divided by d by 2, this is cos theta. Okay. Hence, 2 theta can also be written as 2 cos inverse of this value, all right. So, this becomes, because y we know, d we know, so we are able to calculate actually 2 theta, fine. So, sin 2 theta is going to be 0.4841. So, we have substituted the value, found out the value of theta, and sin 2 theta also we are able to find out. Area therefore, we are able to calculate for this one, it comes out to be 0.1722 meter square. Alright. Now, what the wetted parameter is going out to be? It is simple, its wetted parameter is half d2 theta, correct? It's so r 2 theta, correct? This is 2 theta. We could write r 2 theta or d by 2 r 2 theta. So, therefore, it is going to be 1.055 meter, and the hydraulic radius is going to be A by P, which is 0.1633 meter. So, hydraulic radius we found out, wetted parameter we found out, area we found out, n we already know, S naught we already know. Okay. So, by Manning's formula, Q is equal to 1 by n A into r to the power 2 by 3 and S naught to the power half. If we substitute in the values, we can get Q as 0.1143 meter cube per second. Very simple, just that the configuration. So, the catch in this problem was that the configuration was a little different, other things were fine. Okay. So, we proceed to our next part. So, there is something called best hydraulic cross section. Okay. What is best hydraulic cross section? It is defined as section of minimum area for a given flow rate Q, slope S and roughness coefficient. So, best hydraulic cross section is defined as a section of minimum area. So, if we have been given a Q, slope S naught and roughness coefficient N, it is the best hydraulic cross section is the section of the minimum area, okay, that has minimum area, which gives minimum A for all y, for any depth it gives minimum area. Alright. So, this is the definition of the best hydraulic cross section. We will see some questions as well. So, question is the best is to go for this concept through solving a problem. So, question is obtain an expression for the depth of flow in a circular channel which gives maximum velocity for a given longitudinal slope. The resistance of the flow can be expressed as Manning coefficient. Okay. So, we already know that about the circular channel, because we have already derived it in the last question. All right. So, for a circular channel of diameter d, area is in terms of diameter and theta is given as d square by a 2 theta from previous question. Okay. Wetted parameter is simply d into theta, all right, or half d into 2 theta, it does not matter the way you write, but it comes out to be from . So, velocity by Manning formula is simply 1 by n r to the power 2 by 3 s to the power half, same formula. For maximum velocity, we have to do d d theta of r is equal to 0, hydraulic radius, and that means d of a by p by d theta, or p dA d theta minus a dp d theta. Okay, we can actually find a by p, but it becomes more complex. So, this is much better. This is so p we simply say d theta, and dA d theta will come out to be this, because a we have already found out. A we simply write down and dp d theta will be d, and if we solve this, this will give theta minus theta cos 2 theta minus theta plus half sin theta. This finally will give us simplification that tan 2 theta is equal to 2 theta. Okay. Now, until this point it is simple, but the solution for this is solved using trial and error, and if you do that, theta will come out to be 2 theta is will come out to be 4.4934 radian. I do not expect you to be able to do solve trial and error, but this is the way it is to be done. And if you find out theta, then y by d is given as 1 minus half 1 minus cos 2 theta. Okay. So, this is and this was what was required. All right. All right. So, this is one question. So, another question for the hydraulically efficient triangular section, we have to prove that the hydraulic radius is y times. So, this is what we need to prove. All right. So, the solution is, let the side slope of the channel be m horizontal and 1 vertical. Okay. So, area is going to be for a triangular channel. All right. So, area is going to be what is going to be area? So, area is going to be half base into height. So, 2 cancel, area will be m y square, correct. That is what is written here. All right. And the parameter is going to be very simple. Sorry. So, parameter will be this whole, correct. So, it will be 2 y. So, if this is m y and this is y, it will be y under root m square plus 1, Pythagoras theorem, and the total will be this plus this. So, it will be 2 y, which is written, and what we have done, instead of m here we have used this equation from area. All right. So, our area comes out to be a by y square, and parameter comes out also be in terms of a and y. So, our unknown here is a and y. For an efficient section, what do we need to do? We need to have the dP by dy is equal to 0, fine. All right. So, to be able to do that, we already have this equation in terms of area, fine. So, we do dP by dy and we obtain minus 2 into a e whole square divided by y e ka whole cube plus 2 y e is equal to 0, and on solving this we get y e is equal to under root a e. This is very simple, So, 2 y e is equal to 2 a e whole square divided by y e cube. So, 2 gets cancelled. So, a e square is equal to y e to the power 4. All right. So, a e will be y e whole square, or y e will be under root a e, which is shown here. Okay. So, this also means for efficient channel m is equal to 1, because we got y is equal to under root m, sorry, we got a is equal to my square. This will hold true when m is equal to 1. All right. Hence, P is going to be a 2 under root 2 ye, or AE is equal to ye whole square. All right. Because y is under root AE, or AE is ye whole square. So, in terms of perimeter, you go back. So, this parameter is a square is so what we got was ye is AE is ye whole square. So, ye whole square divided by ye whole square plus so to the power 4, and this will give us 2 under root ye, 2 under root 2 ye, and AE is y square. This is what we got. So, 2 under root 2 ye square, or 2 under root 2 yes. Okay. So, this is what we got. So, AE by PE, that is hydraulic radius, is ye by. So, these questions are quite simple. If you follow step by step, you should be able to solve these questions very easily. So, this is another question. It says that the triangular duct resting on a side carries water with free surface as shown in the figure. Obtain the condition for maximum discharge. So, just telling you, for maximum discharge dq by dy is equal to 0. So, everything is actually given. All right. So, we are going to go a little bit quick, and so this is also actually the calculation for this is difficult, but the procedure is very simple. But our objective in solving is not the difficulty of the calculation. For test or anything, the calculations are not going to be so complex. I want to do it because for this Manning's equation and the coefficient, you should be able to handle different type of cross section. So, this is the triangular, a different type of cross section. For different m is equal to 0.5 and different m is equal to 1.0, we need to find out maximum discharge. All right. So, the solution is for maximum discharge dq by dy should be equal to 0, but q is we know 1 by n a r to the power 2 by 3 and s naught to the power half. We know that n and s naught is constant, correct? We know that. All right. So, simply dq by dy is going to be d dy of a r to the power 2 by 3, because n and s naught are constant, or in terms of a and p, if you write r to the power 2 by 3 as a square to the power 2 by 3, and so a into r to the power 2 by 3, let's. So, d dy is the same as d dy of a r to the power 3 by 3 to whole cube, correct? So, it becomes a cube divided by multiplied by a square by p square, right, or d dy of a to the power 5 by p square, same as what we have written here, just all right. So, where the area is b minus my into y. If you go and look at, it is very simple. This is the area submerged, alright, and this is the perimeter as well. So, okay, I will just, this is the area and this is simple trigonometry. So, you can find out m, this is the area, okay. I will take this out and this is the perimeter, wetted parameter, alright. So, this one, good. So, area is b minus my into y, parameter is b plus 2y under root m square, you can verify it yourself. So, if we put this here, we will get so from this we get 5 p into dA dy, alright, into a to the power 4 minus 2a dp by dy is equal to 0, alright. It is a little more complex actually. And for maximum discharge, if you use this a and p is this, now the calculation becomes very cumbersome. But anyways, if you put the value of once, when you put in this equation value of m 0.0.5 and m as 1, you can see for yourself that this will turn out to be equation like this, 5 b square plus 1 point, very complex, but yeah, and if you solve, this is y is equal to 0.849 b, alright. So, it is a quadratic, so not so complex actually, but it can be complex. When m is equal to 0.1, we get equation like this and y will be 0.4378 b, alright. For m is equal to 0.5, m is equal to, for m is equal to 1. So, see, this question actually is more towards tackling all the possible problems for uniform flow, Manning's equation, wherever they are required, and I think that should be the core thing that you must be practicing this week as well. We are going to start with a newer topic, gradually varied flow and rapidly varied flow, from our next lecture. Okay. So, we will spend at least 3 to 4 or maybe 5 lectures, that depends how fast we go. So, this is enough for today's first lecture of this week. From next lecture onward, for this week we will be dealing with gradually varied flow. Thank you for listening and see you in the next class.